All right, let's get started. Welcome to Robotics 311. It's lecture 5. Today we're going to do some cool stuff. We're actually going to start talking about lab 3 tomorrow. We kind of do a little bit of that. We're going to review that example problem we started and spend more time going through that. And then hopefully we'll get a thermal analysis. If we don't, we'll push that to Thursday. Today, lecture 5. So yeah, planar ballbot modeling, motor selection example, thermal modeling. We get there. As a reminder, we took our complex ballbot problem, and we broke it into a planar model, which just consists of a ball, a single wheel, and a mass. And this looks like a pretty solid representation of a ballbot. We use this because it was easier to compute the torque required in this more simplified version. And we considered this kind of a overestimate, which helped us specify our motor. So we can take this model, analyze its forces, and determine the torque required, which we can then use to specify a motor. We talked about a free body diagram that was like relatively complex, but what was good was that really only one force ended up mattering, and that was force FW2. And then we had some constraints. So those constraints we knew because the ball is not going to slip on the ground. We kind of know we can use the radius to determine the actual movement of the ball and therefore the movement of the wheels. And then we also know that the tilt angle and the wheel angle are going to be related if there's no slipping as well. These were our constraints. Ball velocity just comes from kinematics. These two expressions came from our analysis of a free body diagram, which is what this is called. This is called a free body diagram. It's a little more complicated than what you typically see in an undergrad class. But we're going to simplify it by kind of only looking at the components that actually matter for the production of torque. We kind of put it all into one slide. This is how we go from our specified trajectory. So we specified a motion profile. We can use that motion profile, our free body diagrams, to generate the equations which tell us the torque. We can use that equation to determine for torque to determine the current required. We can numerically differentiate the current required to determine the voltage needed. So this is a voltage and current profile that would be required by this planar ballbot to do what we're actually telling it to do, to roll forwards, up to 1 meter per second. Tx, this came from our expression. This is the torque required to actually move the ball, roll the ball around. This is the torque required to accelerate the inertias. And this is the torque required to overcome the viscous loss. So we're just kind of summing up the different components of the torque that the motor has to do, divided by the torque constant, which tells us the current. And similarly for voltage, we just use Kirchhoff's voltage law. When we did this, we used the motor model from the motor that we're going to use, which we can obtain from Pololu. We can actually determine the current and voltage needed, and they're shown here. This was created using an M file that I posted and kind of walked you guys through. And that is the kind of sophisticated version of the ballbot version of what we're about to do for this example, where we go from kind of analyzing its forces, adding the transmission motor properties, determining the actual current and voltage. This is something you guys should be able to do. So you should be able to take an input or desired motion trajectory, determine the mechanics of the system, and to determine the required current and voltage. On something like a midterm, the mechanics would be either given to you or very trivial. So this class is not a class on calculating mechanics of complex systems, but you should be able to understand how these different concepts work together to determine current and voltage. That's something you kind of will be tested on. And then we wanted to do an example, and this example follows the exact same process. Let's say we wanted to build a catapult robot, and we're thinking to ourselves, okay, like if I want to build a catapult robot, what motor should I use? So the way we did this was we determined the total torque. The total torque the motor has to do, it has to accelerate the different inertias. J was the rotor inertia. ML squared over n squared is the reflective inertia of this giant arm. This is last term, and then this is the torque, the gravitational torque on the mass. If we divide this by K2, we can determine the current, and similarly, we can get the voltage. So we kind of walked through, last time we walked through like calculating, like developing those expressions. Do you guys feel like if I gave you a test right now, and I gave you a problem like this, that you could generate an equation like that? Who doesn't think they could do it? It's okay if you can't. Okay, good. All right, good to know. So let's stop for a second and talk about it. This comes from, like, where did this expression come from? There's a fundamental law we use in engineering. Where did it come from? Close, the other one.
Newton's second law.
Newton's second law. So all we did here was like create Newton's second law for the system that is around this point. So if you're looking at, if there's a mechanical system involved, almost always you're going to start with Newton's second law. So that part should be like pretty standard. There are other ways to obtain the governing equations that we're not going to learn in class. There are more sophisticated ways to determine this. There's whole fields kind of on this concept. But understanding that you have to do Newton's second law, either linear or rotational, that's something I think you guys should be able to do. And then it's, if you can remember that it's Newton's second law, then you just have to figure out, okay, what are the different components of torque or force? So there'll always be an inertial component. You're also always accelerating some mass, so you know there'll be an inertial component. There'll generally, if we're talking about motors, there'll be a viscous loss component. And in general, there should be a modeled loss component somewhere that's typically like exists in mechanical systems. Then this is a gravitational mechanics. This one is the only one that requires like a little bit of more mechanical engineering knowledge. We had to know kind of what we thought, how we were going to do this and model it as a function of theta. But I think it's just force times distance. Like I'm hoping that that's not too ME-centric. Yeah?
Can you go over the reflective part of the inertia again?
Definitely. So reflected inertia. So right now, this analysis is being done where? Like at what point in this like process, flowchart, what analysis, where are we on this analysis? It's with respect to kind of where in the system. Is it after the transmission? No, it's before the transmission. We want to know what the motor has to do. So step one is to figure, like, make that decision. This decision, we could have analyzed this at the output of the transmission. It would just look different. But we made the decision, and that is what I would recommend in this class. You analyze at the motor so that you can go directly to current and voltage. So then, if we're thinking about the motor, it's moving much more quickly than the output of the system. Does that make sense? When the motor's spinning really fast, the output's spinning much slower. So its inertia component must be less because it's not accelerating as much. So hopefully you could get to, okay, there's an acceleration and there's some inertia. The motor's inertia is moving just as fast as this v is motor's angular velocity. So the motor's inertia is moving just as fast. It's going to contribute just like normal inertia times acceleration. But the inertia of the arm, the throwing arm, is on the other side of the transmission, so it's moving much more slowly. In addition to that, we get a benefit of the torque being applied. We get to amplify our torque. So we're amplifying the torque through it, and we're also decreasing the velocity. So the combination, the result of those means that you divide this by n squared. So the inertia on the other side of a transmission gets reduced. And it's reduced by a factor of n squared, where n is the transmission ratio. And so let's say they'll generally be components that are divided by n squared, unless we could have said, well, we think this is really low. Then when we divide it by a number squared, it's going to get really low, so we'll just ignore it. That would not be depending on the exact numbers, but that could be a okay way to now analyze it. But in this example, I want you to see the effective transmission. If we're trying to determine these equations for current and voltage, what's the first equation we start with? You guys already said it. Newton's second law. Step 1, Newton's second law. Step 2, try to determine how many components of torque there will be. So like we know inertia will be there, loss will often be there, and then in this case, there's a gravitational component of load. It has to do with the kind of weight of that arm. So then we're just, once we understand there's going to be inertia, there's going to be loss, there's going to be some weight of that system, then how do we represent that? Hopefully you could go from those thoughts to these expressions. This is probably a little more complicated than what I would give you on an exam, but it's in the same ballpark. So all I did here was substitute n theta for phi and rewrite that expression in terms of theta. Good, so we got to here. I think we should keep going, and then I'm going to walk around. We're going to take like 10 or 15 minutes to do this. I'm going to walk around and talk with you, and that's your kind of time. We're going to move kind of away from this. So this is probably the last thing we're really going to focus on, the mechanics of it. So now's the time to kind of be asking questions or trying to understand, and help me understand how I can make it more clear. You guys come from a very diverse set of backgrounds, so that adds challenge to teaching a class like this. So help me do it well. Okay, so this is what we're going to do. We're going to model the system. I want you to select a motor from the spreadsheet. It was uploaded to Canvas last time. I've uploaded a new M file that has a little more structure, pre-written structure for you. So under like files for lecture, open up a MATLAB example that's like 311 example student or something. You can grab the Excel sheet. I can actually put that in there from the other day. I think it's still in the previous. Days. Files. I'm going to put it. So lecture 5, files for lecture 5. And I put the MATLAB, or I put the motor specs Excel sheet in there again. So let me switch to my computer. It's going to take a second to open MATLAB. So everybody should open MATLAB, download the example, starting a file, and let's kind of like step through this over the next 15 minutes. What you should end up with is a motor that you selected from that sheet. So you picked one, and then you have to pick a transmission ratio that lets that motor be used in a task like this. If, no matter what you do, your current and voltage are too high, then the motor is the wrong size, and it's a wrong motor. These motors should be fine, I think. Everybody has their laptops? So you should see something like this. So this is your file to start with. I've kind of like pre-listed the parameters you have to fill in, and then kind of added locations for you to put your expressions. And then I created some plotting for you. if you use the same variable names, then they'll plot, otherwise you'll have to update the variable names. So I created some subplots that'll help you be able to do this. I'm gonna go back to like this slide so you can see the equations.
Using the other, do you have the other?
Good. What could be more clear?
I guess I just wanted to go through the spreadsheet. I just want to really get everything and then just see what we get.
You would adjust the transition ratio.
Okay.
And this is about like picking a motor transition ratio for a robot for a specific task.
Okay, gotcha.
And this is like a part of the design process.
Okay. Also, are we supposed to remember this, like, to load the map file?
Yeah, let me put that map file in there too. Yeah,
Okay.
that will just load in variables. As a reminder, I gave you guys motion profiles already. So that's in a map file that was also enough before. I'm now gonna also transfer.
Transmission.
Are d theta and dd theta already derivatives, or do we need to divide that by dt?
D theta is a derivative.
Okay.
D theta, did I provide?
Yes, it's over here, I think.
Oh, yeah.
Example. So it's
Yeah, so that takes the
Cool.
derivative.
okay. Thanks.
Yeah.
So I get an output, but I mean I know that like we can change the transmission ratio and everything like that, but even like when I mess around with it, like I get something like this. Just feel like it's not quite right. I just didn't know because it was a catapult. It does need like a lot of pieces. So I go back down to 0, I thought, but it just looks pretty gross.
No, I think that's generally right.
Okay.
What looks a little weird is this drop off, but I think it's probably
Yeah.
fine.
Okay, yeah, because like that's what was throwing me off. Like I know it would make sense that like it needs a
Like
lot of
bigger?
current to get started, but then yeah, it's kind of just throwing me off that it would need to have some more current at the end. But
Well, I think what's going on there is it's decelerating. So the mass doesn't actually
Oh, yeah,
leave.
you're right.
In this
Okay.
example, the mass doesn't actually leave.
okay,
It
gotcha.
just accelerates and stops.
Okay,
And so what you're seeing there is a massive counter torque to decelerate,
Gotcha,
which is
okay.
why that current is
Okay.
like dropping like a rock.
okay, gotcha.
But that looks right.
Sweet, thank you.
Yeah, what motor transmission did you use?
I used the first motor and I used a motor transmission of 150.
Which ratio of 150?
Okay, yeah, like
Yeah.
this looks
Well,
like
your
inductance,
current-
but I just don't know what this
They
is.
were giant.
Yeah.
So
Okay,
that's
cool.
why I got going up and then it kind of at a certain point I think kind of plateaued on the effect it was actually having.
But now
It's velocity and then v is just
lower.
Okay.
so the faster it goes, the more
Side double dot
you
can use
don't
to
know that term was derived, but it's just
Yeah. Yep. In fact, like that should come up like this.
At a certain point, is like a transmission ratio just like too much, like too large?
Yeah, oh yeah.
Because I was gonna say, like, I feel like I have to be making this huge for it to actually.
Well, what's happening is the acceleration will keep getting higher and higher, and the torque to accelerate will end up dominating, and then it won't be the right option.
Gotcha.
And screening,
Yes.
just do it.
And then completing the table, so selecting a transition.
You have the
What's it looking
D dot, the TDT file on the.
It's probably provided. You can calculate it that way, like by taking the division, but also you can measure it, so obviously it's provided. Only one of those doesn't provide that kind of thing.
Yeah.
Create the variables, although it's
To work
provide
an
the really high
equation,
quality.
is the L in the last term? Different L.
Pretty good.
To work that? Oh, I think.
So these all come from here.
They do. They come from there in this case, but they also come from there. You actually always kind of end up looking up the motor and its properties.
Yeah. What do we? Because I had trouble keeping track of the variations. That's what I'm having.
L is inductance.
And that's okay.
So you can go similar to resistance.
Yeah.
J is inertia.
For
Repeating power constant.
that's what mine looks like, and then that's what my voltage and current look like.
Okay.
Those are probably what's in the next time I'll add like a comment.
I think your voltage and current look identical.
As frequently as I do.
Did you overwrite the variable?
Very good, sir.
I think so. So I have. Is this how you did your DI?
Alright, good to know.
I did it as a different variable, but yeah.
Yeah. So I was
Did you just put efficiency as 0?
Using his plot. Why your voltage and
like the first 30 is.
Can I see your VW?
yeah.
That's actually already, that's taking the first derivative of a derivative. So that's your second derivative.
I don't know if there's any other inductances. Inductance termination. I'm guessing that's the inductance. You have to
Psi is equal to n theta, so
Oh, okay.
psi
Yeah, I
dot is
think
equal
it's just
to n
simple.
theta dot.
I think you're.
What about normal theta?
I guess you just shove it in, right?
So you have J plus
And you have theta.
J load
Oh, do we?
divided by n squared times
is
theta n plus b n mgl
It
cosine
should follow the
theta.
same convention that's.
is that similar to that damping?
Yeah, it's just velocity would be damping, like a loss proportion of velocity.
Is ratio. Transition ratio.
So we
Inertia.
Together.
0.0001.
Oh, times theta.
Oh, just testing the different.
0.0001.
looks like we use the same motor.
Say it again.
Like we're just plugging invoices.
Try yeah. Yeah, try like a
Do
larger
the current,
because like that was
like
really
current or time,
Yeah.
the last term of the voltage.
put it at 10.
Using the motor and the equation together and doing the ratio.
That's right. I had like a giant one because I was noticing.
That's like the whole sort of like.
Okay. Oh, okay. I just wasn't seeing that the scaling was so different. So yeah, I had it so large because like I don't think we can quite get a current of 135. I don't think that was quite feasible. So that's why I have it like my factor one is giant, which is like I still don't think we can get a voltage of 35, but at least we can get maybe 6 amps is also kind of too much, but
And then you
Like-
don't necessarily have to do it this sophisticatedly. You could do more.
which end are you using? Wait, really?
I have another
That
value
would be
that's
also.
different.
Transmission ratio would be.
Transient
I think
response.
its transmission ratio would be.
0.001, 0.19, 0.001, 0.095, 250, 0.00016. Yeah, and then 9.81.
Right.
Wait, so the voltages again? What?
Okay.
I think these damping.
The efficiency or the transmission ratio?
And
It is.
Okay, but we don't find that.
So the 0.8 is used in this, or does that go in this equation below?
Different part. I feel like I did some more. Mine starts at 0.
Yes, I don't know. like numerically? No, it doesn't make sense. Never mind.
Wait, let's see what's your
So wait,
How?
J.
B should have.
so
I use J.
how do they know about three hundred?
Is it possible that the units are just use their unit, which is pretty right?
Is
Oh wait.
because when
You can just
T is
integrate
0
I.
and F is 0, right? I'm assuming that's where
Or
it
the
starts.
derivative of I double. Just start to top.
Yeah.
The first one,
Okay.
and then
This value should be 0 because like side
Yeah.
dot side double. Oh no, because this wouldn't technically be 0, I guess.
Yeah,
It starts at 0.
Bring it up.
information for it.
Do you have any questions?
Yep. And
Theta times X. You're doing capital L, isn't that supposed to be LA? Because L happens.
For B, we're
Oh no, you're so right.
He did have it as L in there, not LA, that's what threw me off too.
Oh no, actually,
Do it,
it
but
should be.
Oh, so yeah,
Yeah.
okay. Alright, there we go.
Yeah, that's
wait, so that's just
I'm pretty sure it's supposed to be LA. Like that's the only thing that would make
No,
sense.
yeah, you're right.
okay.
Imagine
So the
what
n
zero
times
is
Yeah.
on the constant.
Got it.
That's something.
Well, that's how it's working then on Thursday, but like those don't look like good graphs. Like
Are you just trying to find a transmission ratio with a voltage and
yeah,
current?
and then I bumped it to like 500, and it's still like
Well, what's our attainable voltage is gonna be like 12 or under, right? I can't imagine.
exactly yeah. But your current also can't be more than like 2 amps. Like
You might want to.
yeah, the mode that we chose was screwed.
Okay.
Yeah. So it just means that we chose a bad mode.
Yeah, I mean, catapult requires a lot of tools.
Yeah, so like if we do a transmission ratio of 600, let's see, no, see that's pretty, I think 90 volts, we can hit it. I think we can hit it.
That's the torque divided by KT.
I don't know about you, but I just carry around a 90 volt battery at all times with me.
Sometimes you got it.
Yeah.
I'm gonna play around with the other motors and see what happens.
Yeah, no, I was actually curious. That's what I was gonna do next too.
Which came from doing the second law.
AT. Oh, never mind. Torque constant.
Yeah. Yeah, that's it. Then you're picking an end, you have to pick an end. We'll take like another couple minutes, but let's try to like get to a place where we can wind this down so we can keep going.
There's not a lot that have the inductance apparently. None of them have inductance. Oh, except for the very end. Do we just guess?
Try
Maybe the blank just means it's the same.
no, it's the end. Do you know what the knee is for? Like voltage, knee, and transmission ratio is.
Yeah. So
Oh, I have no idea.
I guess it's the same because
Okay.
phi is n theta.
I think it's something is really
I don't know what mine looks like.
Did you use the first letter?
Yeah.
Might be like yeah.
Did you?
Yeah.
peak amperage is like 72 amps. That's all we
So
can take.
I'm guessing.
Or like that's
does this mean
like
that the
under
first
peak
letter
load. That's how much it
bad?
requires is 72 amps.
Because the graph does not look right.
Yeah.
Yes.
I know what I
Okay, so
it's the pre.
current goes to voltage. Is that it? Or no, sorry, current.
Isn't that post?
It might be better.
that's
Yeah,
what
you're right. If n dd theta is dd phi.
N would be
transmission.
into transmission ratio, so it'd be theta times n would give you the actual like
That's the
ratio,
rotary.
or like the actual.
Whereas the inertia is under the same.
The
Or I can come back if you.
Yeah. Okay. So
No load current and solve
Yeah.
like stuff.
We're supposed to change the transmission ratio.
right.
Yeah. I think you might, but still it's weird.
other thing is like is used by is that
That's just
Yeah, so well, not arbitrarily, because you're trying to pull, so like, that's a lot.
What if I just make the transmission ratio 5,000?
Transition ratio is not correct. So you need a higher transition ratio.
Why can you
You're gonna
not
make your volt, so you-
comment in fucking?
I think it's if you use the percent signs.
What's Control R? I was trying to figure out how to like.
Yeah.
It should be Control slash, and nothing can change my mind about that.
I agree.
Yeah, so
Don't
you
be
should
like
go with-
any other text editor. No, just be special.
Good job. That's what you should get. Now you just have to do the like fine adjusting.
You mean DD theta?
God,
So they're just putting the photo over there.
Still, I did like motor 32, whatever, and it's still requiring like 12 volts and 18 amps. Yeah, that's true.
I'm literally just trying the second motor so I can like see the.
I'm gonna try this motor 56 one. Why not? Looks, it's giving me some good vibes.
You don't have to do anything. So it just loads the variables in your workspace.
You have 225.
Oh, nice. All right, all right.
That's it.
I think that's the one. Honestly, I think you found it.
Data is provided to you. And you don't, I would do everything else with data.
I don't have it listed. I just use the same one.
If you look on the right side of that screen, there's data is provided. That's the motion profile. So I created that.
Make sure that the max voltage doesn't exceed. Well, actually, KT, I'd like to find the ten what I'm talking about.
KT comes from that spreadsheet.
So we're not solving.
I might have found one.
You're solving for
Like
torque.
that, right?
But KT comes from the spreadsheet.
It does not look like that.
I think I found something that works. Is this supposed to look like somewhat like?
How do you feel about 18 amps and, or excuse me, 18 volts and 11 amps?
I think it looks like.
It's getting there.
What is the largest transmission ratio I'm like allowed to give you?
Oh, I put 0.8.
Okay, 24 volts.
But you can do it either way.
As good as it's gonna
So
get.
with a 500 transmission ratio, around 11 volts, like a little under 20.
Alright, that's decent.
Pretty sure it
After
has to
the torque
under
is the
5
number.
though. So.
You can get like a 24 volt battery. That's where I'm. I got 24 volt and 9 amps.
Oh, that's decent.
You know, it's like a lot more than you should need, but it's getting there.
Yeah.
So all we did on the right hand side was divide that by KT.
Alright, now I'm at 27 volts, 7.5 amps, and I feel like it's fine.
If I just go like, is it like proportional? I'll just keep like going. There it goes. Oh no. They close it's like 10,000.
Oh jeez.
100,000.
That might be a little overkill.
Who doesn't have an answer? Okay, let's keep going. I want, like, everybody should get to a curve.
It's really good right answer, just like an answer.
Yeah.
Maybe just an answer.
That's what it looks like.
Okay, never mind.
But look at so right now your current is low and your volts are high. So you would want to adjust your transmission ratio such that you put those like into the area that you want. This would require you to carry around a 30 volt battery to do this. Does that make sense?
Yeah.
Yeah, so now you just want to adjust those things.
What is the highest amperage that we're allowed to hit?
This would be like up to you as a designer. It depends on like the driver that you're using. We were talking about, we'll have a lecture on drivers. For now, I'd say try to kind of stick around 1 amp, or if it's faster, it could be higher.
Okay.
So this one could be higher because it's fast. Also, like I didn't really match these motors to this task, so like,
Okay, I was
they
gonna
are
say.
be whatever they are.
I was gonna say, like I'm getting some like unreasonable ones.
Okay, probably that last might be a little heavy.
Yeah.
I don't think this is right.
Yeah.
Okay.
Because like this one's needing like 12 amps and 16 volts.
Okay.
That's it. That's all the motors I chose right now.
Nice. Yeah, so that was. I could probably adjust the.
Oh, you can do DT.
So This is like my attempt to
I'm going for 96. Whenever get beef. I'm about to go with here.
I found
because the owner is
I don't know if it's wrong, there's either 400 nominal voltage.
Is that the very end?
It's like right before the end, it's close.
Okay. Yeah, I didn't want to go all the way down there because then I can't like see the column. So shit, I just exited out.
But stall current doesn't really, stall current is
Boy.
kind of not. Depends on how fast they run that test. So stall is like.
Seemed pretty decent. So
You can do a really high stall current for 0 time. That's a little trick that motor manufacturers use.
Does that mean I should like increase the gear ratio, but it's already at 100?
I meant like
You should increase the
the
ratio.
naming
So it is
convention
already
when you
finished.
got it. Like when did you put it?
this damn thing is tiny. We like that.
Oh, I
It's
just
we lose.
So now you're at 70 volts. So like maybe a little much, but generally like, yeah.
Yeah, so that's kind of a problem. Like, does that mean I need a more powerful motor?
In this case you might, but right now you're still some adjusting of that position.
I'm not really sure.
No, it doesn't look quite right.
Yeah.
Maybe your code.
Yeah.
This guy lied to me. He is not the guy.
That should be times. Oh,
Yeah, so
plus LA squared. That should be times. Or square.
well, this file's a custom file,
Try-
so it's not.
Try now. Still remember.
And then like yeah, they're very
Yeah, I think so. Yeah.
Someone started, getting their hands into architecture and they see this. Wow. Million.
40160. Thanks.
Oh, you like this lifetime.
just a good section.
How to pull this one so like it goes and it stops.
I was doing that as well.
So motors just stop moving the current.
I think it kinda does because I'm gonna bet this motor is very tiny and dinky.
They're doing like a hard stop.
Yeah, there's a bar.
Can you plot it again?
Yeah, that's a dinky motor. Okay, so yeah, you're gonna need a lever. The mass weighs 10 kilograms.
Oh, okay. That's something crazy.
And the lever arm is
Transmission
what?
ratios if they're 100 now with
Yeah, it
tiny.
seems a little high.
So
So that means that when it drops down to 0,
like the voltage is the problem.
I think it looks
something
like
else. You're saying that's what I think I see.
100 to 1,000.
I think that just might have to do with the curve that it's supposed to be taking.
I feel like over here it's trying to tell me that it's
Or
feel like
what would it be, higher
relying on
percentage?
it. It is only
There, I
relying
think I got
on
it right.
They look right. I don't know that it's the equation. I think it's something else.
because it's not
Theta
relying on
trajectory?
reverse power, so that kind of bothers me.
GGB, there were like a few.
Yeah, I haven't been to GGB yet. I need to go there after this.
You wait.
I want to go to GP though.
The line is so long.
I was in line before class and then I was like, okay, screw this. I just left.
Yeah, that could,
So,
Yep.
okay.
it could be canceled out by
You just
gravity
plot theta.
and the damn
Plot theta, plot
thing.
theta.
Yeah, I'm not gonna go today because I already saw JQ.
Oh, really?
Yeah,
Um,
over the weekend. They had like a open house at the Wilson Center and they were there.
Like data?
Yeah,
So
just
once
plot
you
theta.
release power on it, it's gonna start being like its own little generator and that's gonna take a lot out of it. I think it's able to just break up its own.
Email sent in one of the mechanical engineering things
Oh.
that I'm in because I thought it was gonna be my I can send you it if you want.
Oh, yeah.
I'm bored. This is so funny. This is so funny. What's your game? OLI.
B.
Current transmission ratio of like 100.
So transmission ratio is
The JPL obsession.
Yeah.
so it's just kind of big. It's just got really big
Ratio
now.
should have the voltage be extremely high.
They did it for the summer?
I'm pretty sure, yeah.
Last time I looked,
If we do like a ratio of like
Well, I think my laptop
There's
is not
speaker
gonna
last
make it.
weekend, they did.
Thank you, sir.
It should be very
Yeah.
Oh, it's so like people apply.
is how related there. Yeah, now the
After career fair, I don't even want a job anymore.
Honestly.
I don't even want to talk to like a corporate person again.
I think it's good.
Is yours working?
Yeah.
Wait, I only see things for spring and fall though.
Oh, really?
Yeah.
So
So I would only do summer,
Oh, wait,
right?
that's the OSTEM.
no, they're getting something different. They're getting something together. The same thing.
Yeah, that's what I'm saying.
It's not JPL?
No,
I'm confused.
I think OSTEM opens later. OSTEM is like massive stuff. Technically separate.
Why is it complicated?
I know.
Jesus Christ.
Well, now I'm gonna apply. Enter. I don't apply so bad. The ladies are telling us about like the projects they're doing, and it's so cool. And then she started giving us like recommendations for the rover because she builds rovers, and we were like,
Something is still kind of over here because I never see it by negative.
Yeah, I mean,
It's not like so just like.
I can, I just don't have the background, so.
It doesn't necessarily, it probably, it won't have a negative voltage because it's always going in the direction, but the current would change.
But for it to like accelerate and then like stop at the end of the motion, wouldn't that require like a negative effort to stop it?
So I had no idea how to see that, but
Oh wait, because it's going the same direction. Wait, shouldn't it
Yeah.
It's always positive over here, so it's.
Something doesn't quite look right,
T, the double derivative.
but it looks really close.
well, actually.
I don't know why
it's
it's listed.
It's strange that the voltage isn't correct. I mean, the voltage is correct, the current is correct.
Yeah, you should kind of go through it. There's a few things that have to be correct or will not work. Okay, who doesn't have a plot? Okay, let's take like, I'm gonna come help you guys and then we're gonna move. Why don't you guys all do
Can I take a look at your torque graph?
You got a plot?
Okay. Yeah.
It looks better than mine.
Okay, yeah. I'm still kind of confused how these grasses like forming. It's earlier, like when I was on them, just very different.
Like there's so many.
You know, like this torque, remember like,
Like this
this
versus that.
fraction on the right, this fraction, the torque is the numerator.
Why is it so different?
It's different. I drink more. Isn't that one for the ballbot? This is versus this one.
Yeah.
Well, because the ballbot has like smooth motion, whereas the catapult like stops
Oh,
at 70.
that's really true.
That doesn't look, that looks like torque you'd have written there, not current, because you don't have it divided by KT. Right?
Actually, I get theta. Where'd you get DT from? Yeah, because I would see like theta or.
It loads it right there.
Oh, okay, that makes sense. Thank you.
It loads that into the shift. Do you guys get to a plot?
I'm still plugging. I was asking about there's the D times IW.
DIWDT?
Yeah.
Derivative. That's DI.
That's what?
That's the equation for voltage drop across an inductor.
For the reactor here.
Get out of my face.
Are you guys applying to any fun company?
Numerically?
You know, other than JPL?
That function will numerically calculate it for you.
Oh, yeah.
They're really cool.
Yeah, I know. It's like 3D printing.
They 3D print rockets.
Yeah.
I guess these are
Yeah,
just
it's
the motors
awesome.
that I'm looking at because these are really flat.
Yeah. They're launching this summer.
Okay.
Like they have internships in Stennis.
Can we just finish that and get to the
Yeah,
talk?
for like robot testing and stuff.
Oh, okay.
I want to apply to those, but I don't have a driver's license. So yeah.
Is that not, that's not for this, the
Yeah,
same
it
motor?
requires like a vehicle to get around NASA's.
Oh, I was
All you
gonna
do
say
is just divide that by KT and that gives you
That's the plan. I get my driver's license, then I apply.
torque. Is that torque there?
Because their applications are open till like November.
Anything that's not one by KT is calculation of torque.
I literally rewrote my application.
Okay.
How hard is it to get a driver's license?
Okay.
It
makes
That's just really
All right.
hard.
Let's move on, or I'm gonna kind of talk through this. We'll talk through a little bit about what you guys got. I got a lot of questions that are like, how do I calculate torque? But like, okay, just on my side, this is what I'm explaining to you right here. This is calculating torque. So like we're using Newton's second law. This is the torque that the motor has to produce, has to counteract all these other sources of torque, moving the inertia around, fighting viscous laws, fighting gravitational weight. This is torque. So you would get that by doing Newton's second law. Then when you have torque, we just divide that by kT. That gives us the current. Okay, so who got an answer they think is right? Yeah, what'd you get? Well, actually, yours was we weren't sure. Let's do one that I'm sure is right. So we got one that we're sure is right. Yeah.
I got that if I need 14 volts and about 15 amps, which
Okay.
is a little unreasonable, but still.
Yeah, 14 volts, 15 amps. What motor did you pick?
The one that was the 96 nominal peak. The order of this. I think the KT motor U8.
Yeah, that's the first one?
15. I can't, huh?
That was the first one?
No, I ended up choosing one later on down the list, just for trying it.
Oh, okay.
It was the KV. Sorry, it was like cut off as KV 1300, I think.
Okay.
1300.
Cool. What happens if you have a different transmission ratio? What happens if the transmission ratio is really high? Not you, actually. What happens if the transmission ratio is too high? What do you see? What's your cue that transmission ratio is too high? Very high voltage. Why would there be very high voltage if the transmission ratio is too high?
Because the motor has to spin significantly faster.
That's right. So this term ends up dominating and becoming a really large number. So that would tell you, okay, if I run this analysis and I get a voltage that's too high, I know I need to lower my transmission ratio. What happens if you run it and the transmission ratio is too low? What will happen? The current will be extremely high. So this is the process of speccing a system. Like understanding what it has to do, what the mechanics are, understanding what task you're giving it. We're giving it a throwing task, so I created a theta trajectory that kind of looked like that. We're doing a throwing task, we understand the mechanics, then we compute our current and voltage and we look at them. If they're too high, we adjust the transmission ratio, or we choose a different motor, which would be another option. What happens, so let's say, so in this case we had 15 amps and 14 volts or something.
Yeah.
So what if we aren't happy with that? What if we think, okay, we've messed with our transmission ratio as much as we could, we're still in an area that we don't like. We still think 14 volts is too high and 15 amps is too high. What could we do then? Choose a different motor, a more powerful motor, a heavier, bigger motor. Right, that will trade those variables into a place that maybe is more comfortable. This is the process we are learning. It's like this, speccing these aspects of your system so that you can then design around them. Yeah.
I was just thinking, considering how much, there's a fixed amount of energy we have to, say, put into the projectile we want to throw, would we eventually reach a point where using, a better motor would really change anything in terms of, current and voltage?
Well, it kind of depends on, what you're optimizing for. There are lots of right answers for, motor transmission combinations. But if you could always kind of keep designing it and refining it and making it. Let's say you wanted to make it, I don't know, it's gonna get too complicated. I'll skip that. Yeah, there's lots of different motor transmission combinations. You just find one that you think works for your application. That would be like the mass or size of the motor, how big it is, size of the motor transmission pair. Those kind of attributes end up playing a big role. Where does the voltage number come from? Or do you guys have thoughts on your voltage number? What if you expect a system to run at 100 volts? Is that good or bad? And why is it bad? Yeah.
You need like a very powerful battery, and it also can be very dangerous.
Yeah, we need a giant battery, and because like battery voltage is created by stacking cells in series, it means we have to stack a ton of them in series. So there's sort of a finite size that has to be. It ends up being extremely large. So lowering the voltage is just more convenient. Typically, like your ballbot systems will operate on 12 volts. The systems we build operate on 36 volts, 24 volts. Somewhere in that range is usually acceptable, but it does come with, in practicalities of creating batteries if they don't exist already. How about current? Where does current come from? Like, where do your limitations on current come from? 2 places. What?
Parallel cells?
I'm going to say, so the current has limitations that are associated with the drive, so we're going to learn about what that is, but that's the circuit component that allows energy to transfer from the battery to the motor, so that drive has its own limits. And then the other way that current comes into play is it heats up the motor. That's what we're going to talk about after we go over lab stuff, is what we're about to do. Does anybody determine the I squared R loss? Yes? Does anybody know what is the I squared R loss? Yeah.
Power.
That's the power loss, the thermal power loss that comes off of the resistor. So the motor's heating up because the resistor is losing heat energy. So this tells you the power loss from that heat energy. If you integrated this, it would tell you the total thermal energy being output by the system. We'll come back to that. Okay. Now we're going to learn about lab 3. What we're going to do now is talk through setting up Solidworks. So we have a handful of slides that are going to go over setting up Solidworks and then kind of using Solidworks. Everybody has their laptops out already? Actually, let me get through the slide and then we're about to go to somewhere. Tomorrow starts Solidworks designing labs. So over the next kind of 2 to 3 to 4 labs, you're going to be working on your computers, building the components, the structural components of your ballbot. How many people have experience with solid modeling or Solidworks? Awesome. How many people have never used a solid modeling program? Okay, awesome. Okay, good. So this class will not teach you to be an expert in SolidWorks. There's actually like a ton of knowledge behind what SolidWorks can do. So this class will give you kind of a crash course in it. You'll be able to build simple things, which I think is kind of the goal for this project. The mechanical parts you need are going to be very simple. So it's not going to teach you to be an advanced solid modeler, but this class should teach you how to know your way around SolidWorks and be able to build the structural components that you want for your future robots. We're going to provide like files, just like we did for the MATLAB, how they were kind of like pre-written stuff. We're going to provide similar files for you in SolidWorks, but you will still have to do a decent amount of modeling. You may, for lab and homework, you may come to office hours. So far, not a lot of people are coming to see me in office hours, which is okay as long as you guys are tracking the material. But lab stuff is things you're gonna have to work on outside of class. So make sure you come to office hours, we can work there, or you can work together in your teams. Here's the plan to do solid modeling. So have you guys do it on your own computers via a remote cane access login. I think this will work. I tried it myself, it works pretty well. So that's the plan. You're gonna access SolidWorks on your own computer remotely. How many people have used Apps Anywhere? Nice. Okay, so if you've used Apps Anywhere, do you do this? Is this how you do it? Okay, cool. So some of you are familiar with this. Okay, so what I want you to do is download the VMware Horizon client at cane.midesktop.it.umich.edu. That should recognize your computer and provide for you the right VMware download. And it works for both OS, for Mac OS and Windows. Training.midesktop.it.umich.edu. When you go there, does it have a screen where you can say like, click here to download VMware? Download VMware. So everyone should be downloading. It's gonna take a few minutes to download. We'll keep going. Okay. When it's downloaded, we'll come back to this. When it's downloaded, you're gonna click, it'll say like, click to add a new server. There's only one kind of button in this little menu, add a new server. We're gonna add kane.mydesktop.it.umich.edu. Although I'm like, I don't remember this being the exact same URL, so that might be, let me look that up real fast.
Excuse me?
Yeah.
So for VMware, for like the Kane Labs, do you know like which virtual like desktop you want us to use? They have like the 8 GB graphics and like the high performance. Do you think it matters?
It should say Kane Labs 2022.
Okay.
Yep. Yeah, it's the same. This is right. Okay, does everybody's downloading VMware, getting ready to add a new server. Then once you add the new server, when you open VMware, you will be able to click on that server. It'll prompt you to log in using your Michigan login. It looks a little different, but it's still your unique name and password. And then then it'll launch you into a desktop computer. And it'll auto launch apps anywhere. So this is where you see like, this is the Horizon VMware. This is the Horizon like VMware client. It looks like this when you open it. That's Kane Labs 2022. That's what you want to select. After you've added the server. And then this is Apps Anywhere, what it looks like when it auto launches. And I've searched for Solidworks. You're going to launch the student instructional version of Solidworks. Watch. Then it does this weird thing where it opens like this cloud paging system and it boots it in the background for a minute, and then when that's ready, you double click on this cloud paging window, and you'll get the hang of it. It actually works really well. What I'd like to do is have you guys actually open all the way to SolidWorks just to make sure we're all on the same page and ready to rock and roll tomorrow. If you have questions or like you're running into issues, that link at the bottom of the lecture will bring you a help page that kind of talks through common issues. Are you guys able to launch SolidWorks? Or are you guys through downloading and all of that? Is anybody not able to open SolidWorks? Or hasn't gotten there yet? You haven't gotten there yet, okay. That's okay. Let's just pause and get everybody here. This is pretty important. We have, so at least for tomorrow for lab, and then we'll give them for you and your kits, we have mice for you with the little scroll wheel. So it'll be much easier. It's really hard to design with the mouse on your laptops. So we'll give you wired USB mice. Good. Okay. How far away are you guys from your launch?
I'm waiting for the.
Which version do we use? Because it's pointing to one but saying the other.
Okay, that's close.
Yeah, it's almost there.
It's the students.
So I'm gonna slow down.
Do you guys care if I keep going?
Yeah.
Okay. Yeah, you have a question?
I don't know if SolidWorks on my computer, is it? We can deal with something they're too big that I would have to go through this, or would that just be fine?
That should be fine as long as it's 2022. Okay. Okay. So you want to use the SolidWorks academic license. Now let's talk through a little bit about what SolidWorks is. Okay. SolidWorks is used to create like 3D representations of parts. It's the beginning of how we make something that looks like these parts. It's how we build the instructions to have these things machined or made through rapid prototyping. You can think of it as like clay, but with mathematical and geometric relationships. So anything you can think to build with your hands, you can create SolidWorks. It's just getting more and more advanced in terms of the operations that you do. There's kind of 2 different levels that I would say of creating a part. You can do a 3D operation, which is something like extruding a rectangle, or you can do a sketch. We'll talk about sketches next. But the way operations are done is first you would select at the top of when you open SolidWorks, this will be the top of a part file. This will say features. These are how you do different feature operations. That says extrude, boss, or base. We're gonna create a sketch of something, and we're gonna extrude it. And that creates a 3D volume. We can also do extruded cuts. Same exact thing, but we're removing material. We can do revolve, where we can revolve something around an axis. All of these operations build 3D parts, or at least 3D features that can create a part. You can do things like walk, or send something around a path, like a worm type kind of like thing. So this tells you like how to create features, so these add material. This tells you like how to do cutting operations, that removes material. If you stack these operations, you can build more and more complex parts. Parts can be added together in something called an assembly. We'll skip assemblies for now, we'll think about just part files, but parts can eventually be grouped together, assemblies can be created with mating relationships. And I've already talked about this. So this is kind of like the 3D operations. Let's say we wanted to create a extruded boss or base. We would click that button. The next thing it would do is prompt us to create a sketch. It has to know like what we're extruding. So the next thing I want to talk about is sketching. When it prompts you to create a sketch, it's going to prompt you to select a plane or a face. It needs to know like what 2D surface does that sketch live on. So the first thing it's going to do is like prompt you for a plane to select or a face. Then it's going to bring you into a different screen, a different little like menu here, the top on the ribbon. So the features is still here, but we're in Sketch. Sketch contains all the sketching tools, which create lines instead of 3D objects. We're creating a 2-dimensional sketch. It's just like kind of drawing with a pen. You can create line segments, arcs, circles, different geometric shapes. You can trim to delete faces or lines. And so here's an example of, let me zoom in and show you the top menu. So similarly, we had sort of like cutting operations. These are like the different shapes that you can use. These are the cutting operations. You can like pattern something. Like the way you'll sort of get the hang of like building structures and working on sketches is by actually doing it. That's what you're actually going to do is kind of get your hands dirty and start doing it. But this will give you at least an overview. So these are the different sketch operations. Anybody know what this button does? Convert. Any SolidWorks users? Convert will take a feature from something else, another like operation, 3D operation, and it'll put it in that sketch. So if I had a sphere and I was sketching on a plane that bisected that sphere, and I click on the sphere and I click convert, it would provide a circle. that is the sphere. So anywhere that the part passes the plane, it will give you a line segment there. So that's what convert does. Offset is similar, except for instead of putting it there, it lets you offset it some distance from that part. So you'll really these are just different sketch operations that are pretty straightforward, but you'll have to play with them, I think, to really get the hang of it. If we look at what a sketch looks like, this is kind of like how sketches are done. That's a sketch that someone's creating. One thing that you're going to need to be able to do when you create a sketch is add dimensions. So the way that's done is with Smart Dimension, which is the button right here. Smart Dimension. That lets you select two lines and add a distance, or select a line here, and add an arc, an angle between them. If you click Exit Sketch, this button, it's kind of depressed. I press that, it's going to back me back out into the 3D shape that I'm trying to create, and ask me how deep do I want this extrusion, for example. So if you do a 3D operation, the first thing it asks you to do is select a plane, draw a sketch. When you're done with the sketch, you hit Exit, and it brings you back out and prompts you for example, how deep does it go, how far, if you're revolving it, how far does it revolve. So you'll kind of build features this way, and you'll have to get the hang of it by messing with it, by actually doing it. Okay, this is the ballbot that we're building. Over the next kind of several labs, we're going to build these mechanical structures. I want to quickly talk through just some of the things that are on the ballbot, so we're all on the same page in terms of what they're named. The top of this, you'll get a 12-volt battery, 6 amp hours. So you have a 12-volt battery. It's going to live here. That battery outputs directly to the motor. Kind of underneath the middle plate will be where your Pico lives that you soldered on lab 1. There's a lower plate we call the base plate. That's where the Raspberry Pi and IMU are going to live. We have 3 Omni wheels. I'll talk about what Omni wheels are soon. So the plan for the next set of lectures, labs are going to be designing this. Lectures after thermal are going to go into information about designing a building. So wheels, structures, machining, that kind of thing. These kind of lines here, those are standoffs. We're going to give you those. So you guys will all have the same standoffs. You'll all have the same Omni wheels. You'll all have the same motors. You'll all have the same battery. You have the same Raspberry Pi and the same Pico. On the left side of this is what you're going to be building. So there's 3 acrylic plate structures here. We call this base plate, middle plate, top plate. They're laser cut. There's 3 motor mounts that mount the motors to the base plate. Those are going to be 3D printed. And then there's one other small acrylic plate, which is a plate that the Raspberry Pi and IMU mount to, or Pico and IMU mount to. And that goes here. So basically we have the Raspberry Pi isolated off the structure, and it's held off by rubber mounts. The motor mounts are more challenging. If you look at this motor, it has a face that's canted at an angle, and then it has to kind of hold that motor, mount up to its bolt pattern, and then it has to kind of have a flange that mounts to the base plate. That's a little more complicated. The different acrylic sheets, those are just 2-dimensional drawings that we'll cut. Those will be easy. What you guys get to do is choose the shapes. So you can choose the shapes of these for your ballbot. You can choose the colors. So you have a handful of different colors. You can choose your shapes. What we will provide is locations for the mounting holes, locations for the Raspberry Pi plates, and that's pretty much it. The rest of it, you guys get to decide how you build it. You all get the same number of standoffs, so your systems will look similar but different. This is the next sort of labs. Okay, here's the base plate template. This is where you guys are gonna start. This is our base plate. There's a bunch of holes on it. Those holes are kind of color coded in this little map. We have isolator mounts. So this isolates the Pico and IMU. The red here, the red and the orange kind of look similar, but this, and that, those are the mounts for the motor mounts to mount to the base plate. And then all of the yeah, I cannot tell what's orange, what's red. The standoff holes are these. So the orange ones are the motor mounting holes. Or I think I have that wrong. The red ones are the motor mounting holes, and the orange ones, unless I'm like not tracking the color perfectly. But there's a handful of motor mounting holes, a handful of holes for the standoffs. The motor mounting holes will come on a template. And the standoffs you guys will get to place wherever you want. There's a certain amount of like bookkeeping that has to be done. Now you're going to be designing plates with stack with standoffs. Those standoffs will have to be located and the holes will have to align. So you'll have to do some kind of understanding and bookkeeping of how is your system laid out. And that'll come through in your Solidworks designs. This diameter I think should be at least 75 millimeters. This ball sits, the ballbot sits on the top of a basketball and it can actually like contact the basketball here. It sits really low. We wanted it to sit kind of as low as possible. So this hole prevents the ball from actually contacting the base plate. This is an example of like what you'll get, except you won't get these. You'll have to put those on there. So you'll get a sketch with these three holes, and you'll have to pattern those at 120 degrees apart. And then you'll have to create a boundary for this. And you can make that shape as interesting or not interesting as you choose. So like it could be all crazy, or it could be a square or a circle like ours. The first ones we did were not circles. They were like a little bit more geometrically interesting. So you guys can do kind of whatever you want. You'll have to pick your colors. Base plate. In addition to the base plate, we have to create the middle plate, which essentially just holds the Raspberry Pi. And then the battery kind of straps to it, and mounts to with Velcro. And then the top plate. The top plate we just use to hold a leash. So you guys are like building a little hook or something. We have ferret leashes. So once you guys get to the part where we're controlling it, it's really unstable. It really wants to fall over. And if it falls over, it can destroy itself. So we have a little leash that helps you like do the control without putting the robot in danger. So you'll have to make all four of these plates. This is the Raspberry Pi kind of mounting plate. What was the purpose of this? Say it on the. Why do we do this? Or what is the purpose of this? Yeah.
Does it reduce heat?
That's a good guess. If we wanted to reduce vibration. So the Omni wheels are not actually round, as you'll see. So when they roll, it vibrates. And that vibration is picked up by the sensing elements, and it just adds noise to the controller. So it just makes a hard task even harder. So one thing we try to do is to diminish that was you can buy little mechanical isolators, which are just rubber grommets with fasteners. So that's what goes here, here, there, and there. You guys can put them wherever. Then these holes, the four blue holes, those have to match a Raspberry Pi. You have to be able to mount a Raspberry Pi. The Raspberry Pi and the Raspberry Pi Pico board have the same mounting holes. So for example, if you were wanting to do that, you might look up like find a Google image search for the layout of a Raspberry Pi. This is one I pulled. It shows that these fasteners are 49 millimeters this way, 58 millimeters this way. So I've provided that for you, but you could like these are the kinds of things that you might have to look up when building this. Reduces motor vibration and impact on IMU readings. The Pi mounting holes have to match the Raspberry Pi layout. This is what we're gonna provide for the motor mounts. So the motor mounts are here and here, kind of shown there. This is what we're gonna provide is there's the 3 holes. This would be something like the base plate. But this is a different part, so we're not looking at the base plate part right now, we're looking at the motor mount part. So the base plate would live in this base plate plane. Or actually, I think it was perpendicular to that, it would be in this plane. And then this plane contains the face of the motor. The motor sticks out inwards. So this face would have to be covered in plastic and have holes for the fasteners to go through. Then it would have to join to a structural element that mounts to these 3 holes. One way you could do that would be extrude up, extrude out, and then cut everything off. For example, like there's lots of ways that you could potentially create this part. The way that I just told you is relatively straightforward. You could also loft, which will connect 2 features through space, 2 sketches through space. But this is the harder. This is a 3D, like a design in 3 dimensions. Everything else is a design in 2 dimensions, which we're gonna laser cut out. This part is in 3 dimensions. We have to 3D print it. It's a little more challenging because it has faces that are canted at angles, which makes it a little more tricky. Are there any questions about this? I'll show this again tomorrow as we kind of kick off Solidworks. What I'd like to do now, we have like 3 minutes. I'm just gonna stick around. I like to make sure people are set with Solidworks. If they have any questions about the example we did, come talk to me. Or if you have any questions about how things are gonna go in lab, come talk to me. Okay? Otherwise, we will see you tomorrow. Make sure you can open Solidworks. I would say, like, don't leave until you know you can open Solidworks. This is gonna be real important.